Welcome to the ePathshala lecture series in computer science. We are dealing with the course computer architecture. So, this module will look at an example which involves branches for dynamic scheduling. So, the previous module we just looked at an example without branches. So, now we look at a dynamic scheduling for a sequence of instructions which also involves branches. So, the objectives of this module are to discuss how dynamic scheduling happens for a sequence of instructions involving branches, and of course, we will do a clock level simulation of the Tomasulo's approach to give a clear idea of how branches are handled, how dynamic unrolling happens, and how these instructions execute out of order. So, before we go into the details of the simulation, we will just quickly go through the basics of the Tomasulo's approach. You know that in the case of the Tomasulo's approach, the hazard detection is done in the reservation stations, because the reservation stations do the renaming process between the registers and the instructions. So, an instruction involves a register operand. This is renamed to a reservation station. So, this renaming process helps us overcome the anti dependencies and output dependencies, and because of that it removes your war and war hazards, and they serve as virtual registers, and the number of reservation stations that we have is normally more than the number of registers, that physical registers that you have, and this helps us solve the name dependencies. So, this is again the organization of the Tomasulo's approach. So, instructions are fetched and put into your prefetch queue. They are removed from the queue and decoded. So, the decoded instruction, once you decode the instruction, you know what operation is to be done. So, accordingly it is allocated a reservation station corresponding to that functional unit. Suppose if the decoded instruction is an add instruction, then you allocate a reservation station entry associated with your add functional unit. You have load buffers which will store all the information about load instructions. You have store buffers which will store information about the store instructions, and all the functional units are connected by means of a common data bus. So, the common data bus broadcasts the data on the common data bus. This will go to your reservation station entries as well as the floating point register file. So, if you look at the three stages of the Tomasulo's algorithm, the first stage is the issue stage, where you get the instruction from the floating point queue, you decode it and check for structural hazards. The checking for structural hazards here is the actual checking of availability of a reservation station. So, if there is a reservation station available, you will go ahead and issue the instruction. If there is no reservation station available, it becomes a structural hazard, you cannot issue this instruction. And remember that if a particular instruction has not been issued, it is a strictly in order issue. So, subsequent instructions cannot be issued. And also during the issue process, if operands are already available in register files, you do the mapping process from the register to a reservation station. So, you read the operands from the register and store it into the reservation station. So, because of this process, what happens is, if subsequently some other instruction goes and modifies the register also, you do not have a problem. So, that is how your war hazard is handled, and it is a strictly in order issue. And once the operands become available, you enter the instructions enter the execution stage, and the instructions will remain in the execution stage depending upon the latency of the operation. So, if it is a 40 instruction latency for that particular instruction, 40 clock cycle latency, then the instruction will remain in execution for 40 clock cycles. And once the execution is over, the results will be written onto the common data bus. It is a broadcast operation that happens on the common data bus. So, the common data bus is different from the normal data bus. So, in the normal data bus, you will have the data and you will have the destination address given. So, the data will be written into that particular destination address. It is a go to bus, whereas in the case of a CDB, it is a data plus the source from which the data comes in. So, it is a come from bus. Say for example, if you are looking at a 4-bit value to uniquely identify the various reservation station entries, then that 4-bit entry indicating which reservation station's data is being put out now, and the 64 bits of data are transmitted on the CDB. And if any of the reservation station entries matches with this source address that is put out on the CDB, then the data that is put out on the CDB will be grabbed by these reservation station entries. This will also go to the floating point register which is waiting for this data. So, now we look at an example with a loop, because the previous module we just looked at an example which has only a basic block without any branches. But you know, branches are very frequent in a program. About 20 to 30% of your instructions are normally branches. So, you cannot exploit too much of parallelism if you are only looking at a basic block. So, you will definitely have to look at going beyond your basic block. You will have to definitely look at branches, branch predictors, and how dynamic unrolling of a branch happens, of a loop happens in hardware. So, we will have to look at all this. All these concepts are discussed through this example. So, we have 5 instructions here. The first is a load instruction which loads from 0 R1, stores into register F0. The second instruction is a multiply instruction which is dependent on the first load. So, it multiplies the contents of register F0 which comes from the previous load instruction. There is a true data dependency there. So, it multiplies F0 and F2 and writes the result into register F4. And again, if you look at the third instruction, store instruction, that is again data dependent on the second instruction, because only the multiplied value that is available in F4 now will have to be stored into 0 R1. So, basically what you are trying to do here is take a data from memory, you multiply it with some constant value given in F2 register, and then put the data back into your memory location. And the last 2 instructions are basically the loop maintenance code, where you subtract the register contents of R1 by 8, so that it points to the next data in memory, and check whether the branch instruction basically checks whether register R1 has reached a value of 0 or not. So, if it has not reached the value of 0, it will go back to the loop and keep executing the instruction again. So, depending on what value has been loaded into R1, the loop will get executed that many number of times. Suppose if you have loaded a value of 80 into your R1 register initially, then for example, the loop will get executed 10 times. It will get decremented by 8 every time. We are looking at a value of 8 here because we are assuming it is a 64-bit data for the MIPS architecture. So, the loop will basically get executed 10 times if you have loaded a value of 80. So, these are the details about the instructions. So, now we look at the latencies associated with these instructions. We will assume for this example, this simulation, we will assume that multiply takes 4 clock cycles. You have load instructions here, a load, multiply and a store, that is your basic block. So, the load instruction, we will assume that the first time the load instruction is executed, we will assume it takes 7 clock cycles to execute, because there is a cache miss there. But subsequent load, it takes only 1 clock cycle because it is a hit in the cache. And we will also show the clock cycles for the sub instruction and the branch instructions, even though they are integer instructions. But in reality, integer instructions just have a latency of 1. So, they are ahead of the floating point instructions. And we will go through 2 iterations of the loop to get clarity of the concept of dynamic unrolling and branch prediction. So, these are the data structures that are maintained by the Tomasulo's dynamic scheduler. We have again 3 data structures, as we have already discussed in the previous module. The first data structure is your reservation station data structure, which gives you information about the instruction. As an instruction is issued, the instruction is allocated a reservation station entry. So, we see that there are 3 reservation station entries for your add or sub instructions, 2 reservation station entries for your mul or divide instructions. You have 3 load buffers which have been indicated, and we have also indicated store buffers here, which we did not have in the previous example, because the previous example did not have any store instructions. And look at the slight difference in your load buffer entries and the store buffer entries. Load buffer entries just have a status field where indicating whether they are busy or not, and it only has an address field where the effective address will be calculated and stored there. Whereas, if you look at the store buffer entries, apart from the status field and the address field, obviously they also have a data field. So, as soon as data becomes available, the data is stored in the store buffer entry, and from there when the execution can start for your store instruction, the data will be passed on from that store buffer entry and a memory access will be done, a memory write will be done, and this data will be written into memory. And you also have an iteration counter here, because we are going to go through 2 iterations here. You have an iteration counter and of course a clock cycle indicator, and initially we assume that R1 has a value of 80, so that the loop actually has to get executed 10 times, but we are only going to go through 2 iterations of the loop. So, the first clock cycle, you have the first load instruction getting issued. So, as usual, when an instruction gets issued, you have a load buffer entry allocated to that. So, the load buffer entry, the status has become busy now. Yes, the effective address, the information needed for your effective address is stored there. So, it will eventually calculate a value of 80 in the next clock cycle and store it there. And because your load instruction has to write into register F0, you indicate that the register result status indicates that F0 is to be written by the load 1 instruction. So, those are the things that happen during clock cycle 1. During clock cycle 2, it is a single issue processor. The load instruction has already been issued. So, you have the second instruction in succession, which is your multiply instruction being issued now. So, when multiply gets issued in the second clock cycle, observe that you have a multiply reservation station entry, which is your mult1 allocated to that. So, the status of mult1 reservation station entry has become yes, indicating that it is busy. The operation is multiplication, and if you look at the operands, not both the operands are available. You have one operand which is available, which is your F2 register contents. So, that is fetched from register F4 and stored in your reservation, fetched from register F2 and stored in your reservation station entry. The other operand, which is F0, has to come as a result of the load instruction, load 1 instruction. So, your Q field indicates there, the QJ field indicates that load 1 has to produce the result for your mul instruction. So, one operand is already available, F2, you do the renaming process here. So, you read it from the register F2 and you already store it in your reservation station. The other operand, there is a true data dependency. So, you are waiting for the load 1 instruction to finish. During clock cycle 3, you have the third instruction, which is your store instruction getting issued. So, the store instruction is issued to the store buffer. So, the store buffer now becomes busy. Yes, the status is yes. The address has to be calculated. So, the information needed for address calculation is given there, but the data is still not available. The data is, there is a true data dependency with the mul instruction. Mul instruction has not yet even started execution. So, the data field indicates that mult1 has to produce the result for the store. And similarly, if you look at the register result status, F0 indicates that load 1 has to write into it, F4 indicates that mult1 has to write into it. Of course, store instruction is only a memory write operation, so you do not have any changes in your floating point register file. So, this indicates the data dependencies. So, the load instruction has to produce the result for your mul instruction, and the mul instruction has to produce the result for your store operation. So, that is indicated here. So, during the fourth clock cycle, you will have to go ahead with the next instruction and assume that, observe the fact that the implicit renaming that we have done actually sets up the data flow graph. So, you look at the fourth clock cycle, wherein the fourth instruction is being issued now. The fourth instruction, as I already mentioned, though we are looking at the floating point execution unit here along with the reservation stations, just for clarity's sake, we are also looking at the clock cycles in which these instructions are getting, these integer instructions are getting issued. So, the fourth clock cycle, you have your integer instruction, sub instruction getting issued. No reservation station entry has been indicated here because the integer instructions are handled separately. So, the fourth clock cycle, your sub instruction is getting issued. So, you are dispatching the sub instruction which is not available in the floating point queue, and the fifth clock cycle, similarly you are going to give your branch instruction, you are going to dispatch your branch instruction. So, the branch instruction again is an integer instruction. So, just for clarity's sake, we are showing the branch instruction here. So, the branch instruction is issued to your integer unit. So, branch is also not in the floating point queue, but that has been indicated here. So, when you move on to the sixth instruction, sixth clock cycle, we've already issued 5 instructions including a branch instruction. So, you have a dynamic branch predictor there. So, the branch predictor will predict the behavior of the branch, and in this case the branch predictor most probably predicts that the branch is to be taken, because after all it is an iterative loop which will have to get executed a number of times. So, the dynamic branch predictor predicts that the branch is to be taken. So, we have to go, it does a dynamic unrolling of the loop, and we will have to go and fetch the next load instruction. So, based on the branch predictor, the next load instruction would have already got fetched, and we issue the second load instruction or the load instruction of the second iteration. So, the load instruction of the second iteration is issued here. So, you can observe that the load 2 instruction is issued to your load 2 reservation station entry. So, you have multiple loads which are outstanding. They have, because load 1 has already not completed. Load 1 has not completed because we assume that it is a cache miss and it is going to take 7 clock cycles to fetch the data from the next level of cache or main memory, whatever it is. So, load 1 has still not finished, but load 2 has been issued. And look at the fact that load 2, if you look at the register result status, you find that F0 is to be written by your load 2 instruction now. Earlier we had assumed that load from the first iteration is to write into F0. Now we've overwritten that, and we are indicating that load 2 has to produce a result for F0. So, that is how your this renaming process actually solves your output dependence also. So, both instructions, although they have the same output register, once the second instruction or the later of the 2 instructions is issued, we indicate that F0 is to be written by your load 2 instruction now. That is an important observation to make. So, you will have to observe that maybe F0 never sees the data that has been loaded from the load 1 instruction of the first iteration, that is from location 80. So, F0 will never get the data, and now F0 is to get the data from memory location 72. So, if you look at the next clock cycle, clock cycle 7, we are again issuing the multiply instruction from the second iteration, because the loop has already been dynamically unrolled based on the branch predictor. So, your load instruction has already been issued from the second iteration. So, now we are issuing the mul instruction from the second iteration. So, you find that a multiply reservation station has been allocated. Of course, the data operands are, both the operands are not available. F2 operand, which is a constant value, is anyway available. That is read from your register file and stored into the reservation station entry. But the other operand has to come from the load instruction of the second iteration. So, it indicates, that is indicated in your QJ field as load 2 to produce the operand for your mul2 instruction. So, the register file is completely detached from the computation, and that is how your problems of renaming has handled your war and war hazards. And you find that the first and the second iterations are completely overlapped. So, even though the first iterations instructions, all the 3 instructions have not yet completed, you find that we have completely overlapped the instructions of the second iteration as well. So, in clock cycle 8, you are supposed to issue the third instruction, which is a store instruction of the third iteration. So, the store instruction is again issued by allocating a store buffer entry there. So, the store 2 buffer is allocated there. So, the effective address, which will eventually get calculated to 72, that address, that information is given there. And the result of the mult instruction, the mul2 instruction or the mult instruction of the second iteration is to write into your store buffer. So, that indication is given there, indicating that mul2 is to write into this register, into this store 2 reservation station entry. And if you look at the reservations result register status, you know that F0 has to be written by load 2, and similarly mul2 F4 is to be written by your mul2 instruction, because it is the second iteration of your loop. So, that F4 has to be written by your mult instruction. So, now clock cycle 9, the first load instruction finishes. the first load instruction was issued in the first clock cycle, it would have done an effective address calculation in the second clock cycle, it would have started executing in the third clock cycle. So, third clock cycle to ninth clock cycle, it remains in execution because we assume that it has a latency of 7. So, ninth clock cycle it finishes execution. Ninth clock cycle, when it finishes execution, at the same time you also have the sub instruction of the second iteration being issued in the ninth clock cycle. Now, once your load instruction finishes execution, you know that your mull instruction is waiting for it. So, the mull instruction is now going to take the data that is produced by your load instruction, and of course, ninth clock cycle we are also dispatching the sub instruction of the second iteration. So, the 10th clock cycle, the load instruction already finished execution. So, the load instruction writes its result in the 10th clock cycle. So, the data is transmitted on the CDB. So, that data will now go to the multiplier reservation station mult1, which was waiting for it. That observation has to be made, and because the result has already been written, execution is over and result has already been written, you observe that the load reservation station is now made free. So, load 1 status has been marked as no, and 10th clock cycle you should also be able to issue the second branch instruction, that is the branch instruction of your second iteration. Also observe the fact that your sub instruction and integer instruction was issued in the 4th clock cycle. So, the integer instruction will get is issued in the 4th clock cycle, it finishes in 5-6, it will finish execution. The branch instruction has a data dependency with that. So, 7-8 the branch instruction will execute. So, the result will be available, the modified register value will be available in the 8th clock cycle. So, the effective address calculation for your load instruction will happen in 9, and because we assume that the second load requires only 1 clock cycle latency, it will finish execution in 10. So, the 10th clock cycle you find that the first load finishes execution, writes its result, and the second load has also finished its execution. So, that is the observation that you will have to make. Load 2 is now completing. So, when load 2 is completing, you know the instruction that is waiting for load 2 is none other than your multiply instruction of the second iteration. And assume that we are also dispatching the second branch instruction during the clock cycle 10. So, clock cycle 11, the load instruction has already finished execution. So, it is writing its result on the CDB. So, once the second instruction, load instruction writes its result on the CDB, the data becomes available for the second multiply instruction or the multiply instruction of the second iteration. So, next load in sequence, you will have to bring in the next load, which is the third iteration of the loop. 11th clock cycle, the second load instruction of the third iteration is issued, and 12th clock cycle you are supposed to issue the multiply instruction of the third iteration. But if you make an observation here, there are only 2 multiplier reservation station entries available, and because both the multiply instructions of the earlier iterations, both mult1 and mult2 are still busy with the first 2 iterations instructions, you do not have a reservation station available here, and because there is no reservation station available, you can't issue your mult instruction of the third iteration. So, the mult instruction cannot be issued here, you will have to wait for the mult reservation station entry to become available, and because mult has not been issued, you obviously cannot issue the subsequent instructions also because it is an in order issue. So, clock cycle 13 you cannot issue mull, you cannot issue store, nothing happens in clock cycle. So, third store is also not issued here because the earlier mull has not been issued. Clock cycle 14 your mull instruction, first mull instruction finishes, because you know the mull instruction, the data becomes available at 10, the result has been written by your load instruction in 10. So, this will start executing in 11. We assumed a latency of 4 clock cycles. So, 11, 12, 13, 14 it will execute. So, it will finish execution, and the 15th clock cycle it will write. So, multiply is finishing in the 14th clock cycle. The first store instruction you know is waiting for the mull instruction to finish. So, 15th clock cycle multiply finishes execution and writes the result. So, write CDB happens in the 15th clock cycle, and observe that your mult reservation station mult 1 is now freed up. Because mult 1 reservation station is now freed up, it is possible for you to issue the next instruction. The next mult instruction of the third iteration can now be issued. So 15th clock cycle, the mult instruction finishes, and the store instruction can now go into execution. So mult is completing, the data will be available to your store instruction now. So 16th clock cycle, the store would have already calculated the effective address. So 16th clock cycle, store can do its memory access. So once store does its memory access, it finishes. That is there is no write result part. You don't have to write to the register file, you only have to write into memory. So the store instruction finishes there, and you observe that your store buffer entry can also be released after that. And if you look at the iteration counter, that has also been appropriately indicated here. The mult instruction, the second mult instruction finishes execution in the 15th clock cycle, and it writes result in the 16th clock cycle. Because you can observe that the second load instruction finished in clock cycle 11. So the second multiply instruction will start executing in 12. So 12, 13, 14, 15 it will finish execution, and the 16th clock cycle it will write into CDB. So once it writes into CDB, you know that the second store can also finish. So the 17th clock cycle, the second store of that iteration can finish. So you find that the store of iteration 2 completes in the 17th clock cycle. And now because your multiply reservation station has been freed up, you are able to issue the subsequent instructions because multiply has been issued. So you have issued your mul, and now you have also issued your sub instruction in the subsequent clock cycles. And this is the complete status that has been shown. So we have shown it for 2 iterations here. So the load instruction is issued in the first clock cycle. It does an effective address calculation in the second clock cycle, but it finishes execution only in the 9th clock cycle because it requires 7 clock cycle latency, and writes the result in the 10th clock cycle. And after that result becomes available, the mul instruction starts executing, finishes in 14 and writes result in 15. And the store instruction is dependent on the mul. So it, even though it does an effective address calculation before that, it completes only in the 16th clock cycle. And if you look at the subsequent iteration, the second iteration, load instruction is issued in the 6th clock cycle, but it gets execution completes only in the 10th clock cycle, that is after the previous branch instruction has been resolved. So the branch load instruction is fetched in the 6th clock cycle itself, that is before the branch has been resolved, but the load instruction can execute only after the branch has been resolved. So we assume that the branch gets resolved in the 7th and 8th clock cycle. So 9th and 10th clock cycle, the load instruction executes and writes its result in the 11th clock cycle. The second mul is dependent on the second load, so it starts in 12 and finishes in 15 and writes the result in 16. The second store is again dependent on the mul, so it finishes after the mul finishes, it writes the finishes execution memory access in the 17th clock cycle. So there are a number of observations that you will have to make here. So though we are looking at the same registers being used, load uses the same register F0, mul uses the same register F4, and store uses the same register F4. But we know that the renaming process maps these instructions destination registers to other reservation stations, not the same reservation stations, and because of this renaming process, we are able to completely overlap the various iterations of the loop. So you have a complete overlap of these iterations that can happen, and that depends upon the dynamic branch predictor that you have, because the dynamic branch predictor is going to give a prediction about the branch, and based on that you are going to do a dynamic unrolling of the loop, and you are going to do a renaming process also. So all those are again important observations. Again observe that you do an in order issue, out of order execution, and out of order completion. And in our simulation we observed that a multiply instruction of the third iteration could not be issued because there was not we did not have a free reservation station entry available. So if multiply gets stalled at the issue stage, subsequent instructions also cannot be issued. So we are strictly looking at an in order issue we are looking at an out of order execution and we are looking at an out of order completion. And all this is possible because of the dynamic branch predictor that we have and the register renaming process that has happened. So, because of the register renaming process, we are able to overlap multiple iterations that use different physical destinations for registers, which happens because of your dynamic loop unrolling. And the reservation stations permit instruction issue to advance past the integer control flow operations, and you are also able to buffer the old values of registers. So, this totally avoids the war stall that would have happened otherwise. Other perspective that you can look at here is the fact that the Tomasulo is building the data flow dependency graph on a fly. So, Tomasulo's main advantages, as we already discussed, is the distribution of the hazard detection logic and the avoidance of your war and war hazards. Of course, all this, whenever you are looking at loops involving branches, everything depends upon the accuracy of the branch predictor. Because the branch predictor predicts that the branch is going to be taken, you do a dynamic unrolling of the loop and get the next instructions from the next iteration. Suppose if your branch predictor prediction proves wrong, then whatever fetch you have done is going to be of a waste. So, the performance improvement basically depends upon the accuracy of the branch prediction. So, to summarize, we have looked at an example for dynamic scheduling with branches. So, the earlier module we looked at a sequence without branches, but you know you cannot do away without branches. So, this module we looked at a sequence where you had branches. We observed the fact how branch predictor is used, and because of the branch predictor's outcome you do a dynamic unrolling of the loop, and we find that different iterations of the loop can be completely overlapped because of the dynamic unrolling process and the register renaming process. Because even though you have the same registers for all the different iterations, the renaming process maps them on to different reservation station entries, and that is how you are able to overlap different iterations of the loop. So, we fetch instructions beyond the branch and issue them, but remember that these instructions are not executed. Observe the fact that even though we fetched instructions based on the branch predictor, say for example, the load instruction of the second iteration and the mul and the store instructions were fetched based on the branch predictor's outcome, but the load instruction of the second iteration will be executed only after the first branch gets resolved. So, we only fetch and issue instructions beyond the branch, but we will not execute instructions beyond the branch. Because if we do an execution and if it happens to be a wrong execution, we do not have any means of undoing whatever operation we did. So, we just assume that instructions beyond the branch will only be fetched and issued, but execution will not happen. Thank you.